Okay, well, firstly, I'd like to apologize to anybody who was expecting Mr. Ross Donaldson to present this. Ross is actually in Oxford at the moment. He's presenting the same sort of work as part of the UK's Quantum Communications Hub. The Quantum Communications Hub is a partnership or a collaboration between the series of major academic institutions and commercial companies within the UK focusing on driving quantum communications forward. So unfortunately, Ross couldn't be here today. I'm Dr. Robert Collins, and I'll be presenting this work instead. So I'm an experimentalist, and I'll be giving a more glass on the bench viewpoint of what you saw in the previous talk from Erica. And digital signatures, as I think I don't need to tell this audience, are widely used in the world today. They're buried deep in your email options. I think so deep Microsoft doesn't want you to use them, but they are there if you want to actually sign your email messages. And there are a number of standard protocols that can be used for these. I think we've all heard of RSA, DSA, and elliptical curve digital signature algorithm. But the problem with all of these standard algorithms is that the security relies on computational assumptions. That means that we assume that there are certain functions that are hard to compute one way, they're easy to compute one way, but hard to invert unless given certain prior information. But there's no guarantee that these functions will always be hard to invert. We may come up with new algorithms to allow us to invert them, or we may improve our computational hardware. And all of the messages that have been signed using these methods will then become breakable. So it's a retroactive security break. Just to recap Erica's talk as much as I possibly can in one slide, quantum digital signatures are different from quantum key distribution. In quantum key distribution, you have one pulse or one single photon is used to secure one bit. In quantum digital signatures, it's many pulses, which may be coherent states. In our demonstration, from here on in, they'll be coherent states, but they don't necessarily have to be, are used to sign one bit. And in our case, Alice has to know what they are, but they're not known to anybody else what they are until she reveals some classical information later. And that classical information is revealed at the message transfer stage, which may take place a long time after the coherent states have been transmitted. And this is information theoretically secure. So as we saw in the previous presentation, the first protocol was outlined by Gottesman and Chung in 2001. It was 2006 when Erica, Curti, and Jex came up with the protocol that's sort of practically implementable, and that's what we started working on in 2012. Then, if this actually starts working, there we go. In 2014, we then worked on a version which didn't require quantum memory, and then just recently we've been working on a new version which operates over long distances. And it's these three last papers that I'll try and summarize as much as possible in this presentation. So in this presentation, I'll start by looking at what we used, which used what we call active state discrimination, and I'll explain what that means when we get to it. Then passive state discrimination, which was the unambiguous state elimination or unambiguous state discrimination that you saw in the previous talk. Then some improved symmetrization protocols, which allowed us to go to longer distances. And then finally, I'll wrap up by just looking at a future outlook for experiments that we're looking to do. So the first demonstration used the multiport design that was in the original paper from Erica. And she alluded to that in her presentation. I won't go into it in great detail, but essentially it allows us to carry out the symmetrization of the coherent states that are transmitted between the two parties. Now we've actually built this an optical fiber, and we used air gaps, fixed air gaps and adjustable air gaps to allow us to compensate for any path length drift in the interferometers. At the receiver, we've got silicon single photon avalanche diodes. We used silicon single photon avalanche diodes because they gave us a good noise equivalent power for the experiments we wanted to do. This meant that we then had to operate at a wavelength of 850 nanometers at the source to provide relative compatibility with the optical fiber and the detection efficiency of the detectors. So we used a vertical cavity surface emitting laser at a frequency of 100 megahertz, and that of course means that the optical path length delay there is 5 nanoseconds or half the period. And this is just the standard asymmetric Mach-Zehnder interferometer that's used in many phase-based quantum key distribution systems. So we have our phase modulator here to set the states, and then at the receivers, think the battery's going on this. At the receivers, we then just reverse the process, and we have silicon single photon avalanche diodes to detect the states. Now, as we implemented this design, there was a small flaw with it. We immediately phase modulated here with the signal that was exactly sent on this phase modulator here. So as I said before, there should be some length of time between the transmission of the states from Alice and then the transmission of the message. We didn't immediately do that. So we would have wanted some form of quantum memory there, and in fact, we just had a short length of fiber. As we'll see later, that's actually just a flaw in the way we implemented it, and it's not a flaw of the protocol. So taking a look at the results, we've got there the raw signal rate across the detectors at one receiver, and you can see it goes up to about sort of 2 megacounts per second. Then there's the multiport null port rate is what we should have 0 counts if the system is being completely honest and Alice sending the same signal to Bob and to Charlie. And because this is a real system, we actually had some leakage from our non-perfect visibility, so we had some counts on there even when Alice was being completely honest. Now, we didn't actually use any form of polarization routing in this design, so we had to time gate our results, and therefore we have a sifted rate there on both ports, which is slightly lower. The encoding error rate is just the number of incorrectly decoded states over the total number of states, and from our theoretical predictions, it should hover around about 2.5%. You can see it's pretty much that sort of value there. I should point out that if I show any dashed lines in any of these graphs, those are theory, and then any experimental data points are shown by solid data points. Now, as I said, in the way we designed this, we had a requirement for a quantum memory at this point, but it was a flaw of how we implemented it. We could have just actually set this to flip between the two different basis sets, and that would have allowed us to eliminate that need. However, when we came to repeat the experiment, we decided to instead go to using unambiguous state discrimination or unambiguous state elimination instead of that, and this is the setup shown for it here. We used 2 Mach-Zehnder interferometers, again, with silicon single photon avalanche diodes. And we also implemented polarization routing to get rid of the problem of the sifted rate as well. So just to explain how the unambiguous state elimination works, we've got our 4 detectors and our 2 interferometers. We lock off a fixed phase difference in one interferometer of pi by 2. Then if we take a look at the table of possible events across the detectors, taking a look at, for example, the example of pi here, we can see that the detector which we've labeled as being not pi must not fire. The detector for not 0 can fire, not 3 pi by 2 can fire, and not pi by 2 can fire. Now, if we wanted to do unambiguous state discrimination, we would, of course, need this complete pattern of 3 firing and 1 not firing, which, given that we're working with weak coherent pulses at the source, and then we have a high-loss multiport, and then approximately 8 to 10 dB loss across here, plus about 42% detection efficiency on these detectors, means that the chances of actually receiving these 3 events and 1 anti-event is incredibly small, which is why we then looked at unambiguous state elimination. To sort of quantify that a bit in a graph, this again is the raw rate, very comparable to what we had in the previous experiment. But here now we've got the unambiguous state discrimination success rate. This is when we had the 3 clicks and the 1 anti-click on the detectors. And you can see that it's considerably lower than our raw detector rate across there. But more troublingly, our failure rate when we accidentally eliminated the correct state is very comparable to the success rate. If we then go to unambiguous state elimination, when we're only looking for 1 of those detectors to fire to just eliminate the incorrect state, you can see that we have about 84% of the raw signal rate for our success rate. Our failure rate, of course, correspondingly does go up as well, but it's a much smaller fraction of the overall rate. And in this case, this means that it takes us approximately between 10 to the 14 and 10 to the 28 pulses to sign a single half bit in our message. Now, the problem with these designs is that they use the optical multiport. And this design has about 8 dB loss as we implemented it. That's actually shown there in real fiber, quite a difference from the idealized system there. You can see that there's a lot of different splices in it. There's a lot of different cards to try and stabilize out the fibers. It's not exactly the most stable system in the world, and we had to try and keep it stable for a long length of time while we were doing the experiments. Also, we had to try and make it as small as possible to allow us to keep it stable, which means that the path lengths between each of the parties are only about 5 meters, which is a strict limitation on the size that you can operate this. So we required a new protocol to allow us to operate on long-distance communications, and as was covered, that was outlined by Walden et al. In that paper there. And this one removes the multiport by carrying out the symmetrization on the states after they've been unambiguously state eliminated here at the receiver. And it's the analogy that was given of the jar of marbles. So taking again a look at the results on this now, we can see that we were able to push out to 500 meters, which was a 100-fold increase on the distance that we transmitted in the previous case, but also out to 1 kilometer and even out to 2 kilometers. And this was just limited by the fibers we had available in the lab. We can, in fact, in theory, go out to longer distances. We just didn't have those available. I should also point out that these little points that are tailing off just here at the end, they're just down to nonlinearities in the detectors we used, and they are just sort of removable from this. So to summarize the experimental outlook, the optimization of the experimental parameters will allow us to improve the time taken to generate a signature. And we're looking at improved protocols, which will allow us to generate a signature, which are again summarized in Ryan's poster, number 53. We can also change the operating parameters to increase the transmission range. Now, as I said, we worked originally at a wavelength of 850 nanometers to give us compatibility with the silicon single photon avalanche diodes because they gave us a good noise equivalent power. However, we've now actually gone out and we've found detectors for use at telecoms wavelengths of 1550 nanometers, which are relatively low dark count rate and relatively high detection efficiency. And those should allow us to operate this at the telecoms wavelengths as well. And that's our next goal with this. We're also looking at low-loss systems for implementations on a chip, and we saw presentations on quantum systems on a chip earlier, and that's part of the Quantum Technology Hub partnership, so we're looking at working with them to produce these systems. And also we're looking at theoretical models of the QDS systems, as covered in poster 54, which will explain where exactly we're going wrong in our implementation and allow us to improve things. Thank you very much for your time.
Thank you, Dr. Collins. And now the session is open to discussion. Any questions or comments, please? Yeah, I have one. So in the last experiment, are there 2 parties or 3 parties?
In the last experiment, there's the sender, Alice, and then the 2 receivers, Bob and Charlie. Just didn't show Bob in this diagram simply because it's exact duplicate of Charlie. But there's 3 parties. So Alice sender, 2 receivers, Bob and Charlie.
The distance between Bob and Charlie can be arbitrary because they only communicate classically.
Sorry?
Distance between Charlie and Bob can be arbitrary because they are only communicating with classical channels.
We only tested it up to the distances we did because of the fibers we had, but certainly they can, as long as you can do the transmission over that distance, then yes. It's all.
Thanks.
How does the scale to a larger number of users? What's the scalability? Is it exponential or?
Scalability to a large number of users. Unfortunately, I wouldn't entirely be able to answer that question. I'm afraid it's not my area of expertise. Sorry. I think perhaps if you want to speak to Erica about that, she's perhaps more able to talk to you about that.
Thanks. Then another question. Could you distribute the states sequentially, or do you have to do it at the same time?
To each party. With this design, we did them to both parties together. Off the top of my head, I can't see a reason why you can't do them at different times, provided because they're only storing classical information. So as long as they can securely store the classical information, I don't see any reason why there couldn't be a significant delay between the 2.
Any other questions? We still have a little bit of time, so.
Yeah, thank you. So in this scheme, what was the average photon number per pulse, and what did you do with events where both Bob and Charlie would have gotten a click?
Right, so you can see that we swept the mean photon number from here from 0 photons per pulse up to 1 photon per pulse. In the cases where they both receive a click, you're not looking for coincidence events between Bob and Charlie, so it's absolutely fine for them to receive a click on that. They'll deal with that when they carry out the classical symmetrization protocol. If they choose to send the states to each other, then they will send those measurement records on, or if they choose to retain them, they will retain them. There's no problem with them both simultaneously receiving events. That 50-50 beam splitter there is just to force the two parties to receive the same signatures in this outline, in this design.
Okay, any other questions, comments? If not, then let's thank the speaker again.